Okay, well, it's time to start. Good morning to those of you on the West Coast. Good afternoon to those of you joining us from the East Coast, and a good evening to anyone joining us from Europe or stations further east. And a very warm welcome to you all. Thank you for joining this, the 13th of our regular series of short courses on pumping topics. This one is going to last about 30 minutes, allowing us plenty of time for a Q&A session after the presentation. This is session 13 now, and I expect that most of you will have attended one or more of the previous sessions. So I'm going to forego the usual 4 or 5 slides reminding you of who we are and what we do, and I'll move straight on to the topic at hand. The slides I'm not going to bother to show you will be in the are at the end of the presentation if you want them, and they'll be in the PDF copy that you all receive, so you can peruse them at your leisure later. Let me restart the screen share now. Okay, well, here is a listing of all the previous short courses we've run during the last year. If you've missed any of them, you can get a copy of the materials from our marketing department. Please send an email to info@rawpumpin.com referencing the short courses hosted by Simon Smith. And they will send you the missing information. Well, this seminar and the next one together are going to look at performance testing and inspection of centrifugal pumps, with particular emphasis on API 610 pumps. Now, as with the previous 2 sessions on vertical pumps, I quickly realized that this was too big a subject to cover in one 35 to 40-minute session, so I've divided it in 2. In this one, we're going to look at performance testing, the what, the why, and the how. And then in the next session, which will be session 14 in 3 weeks' time, we'll look at the various inspections and tests that are frequently specified on the data sheets. We'll be holding a Q&A session at the end of this session. So please use the Q&A facility at the bottom of your screen to ask any questions or make any comments. I'll address those that I can live at the end of the session, and the rest we'll address by mail in the coming days. We are recording this session and we'll make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow, complete with my speaker notes. Also, the Q&A summary from both of today's session, this morning's session and this afternoon session. Afternoon for me. Okay, so it's pump performance testing. Here is a typical test stand layout according to the Hydraulics Institute standards, which is also what API 610 requires. We'll go through each part in the following slides, and at the end of the session, we'll show you some photographs of a couple of the raw pumping test stands. So the suction tank. Suction is taken from this tank and returned to it, thus maintaining a constant level and constant suction head. The tank may be above ground, as shown here, or below ground, a below ground pit for vertical pump testing. You may need a booster pump, particularly if the tank is below ground. Flow meter may be in the suction pipework, or more commonly here in the discharge pipework. Suction piping and valves need to be good for vacuum, as NPSH testing will require that. Note that when we performance test, we don't try to simulate the datasheet specified suction pressure, only the specified differential head. Okay, the discharge piping Now, in most test loops, the flow meter is on the discharge side of the pump. And in most test stands, only the pump, complete with mechanical seal, is tested. No base plate, no job motor, no sealing system, no lube oil system. These form part of a complete unit test. It's often called a string test, which may be offered if specified. But more on that in the next session, session 14. The discharge control valve and possibly a heat exchanger to maintain the temperature of the water in the loop below 130 Fahrenheit. That's likely to be necessary if you're talking about high flow, high pressure pumps where quite a bit of energy might be being put into the water. Finally, it goes back to the suction tank. Minimum retention time in the tank is 2 minutes to allow turbulence and aeration to settle. If it's a below ground pit, it's probably much larger than that, and so you've got a larger residence time. Now, when NPSH testing is required, the suction vessel needs to be sealed if you're going to use a vacuum pump to reduce the suction pressure. Otherwise, you'll need to use the suction valve throttling technique. Either is acceptable to API 610. The vacuum suppression method is considered by most people to be more accurate. Now, I will cover NPSH testing in a few minutes, but here is something to think about over the next few minutes. This NPSH test setup is fine for a horizontal pump or a vertical inline pump, but how do you NPSH test a vertically suspended pump, type VS1, VS3, VS6, where the suction tank is an underground pit and there's no valve on the pump suction? So how do you do the NPSH test then? If you've got any ideas, put it in the chat box to make your suggestions, and I'll give you the answers in 5 or 6 slides time when we get round to that one. Here is the way we NPSH test within the Ruhr-Pumpen organization and the main factories. Tulsa in Oklahoma does suppression type vacuum testing. Monterrey, Mexico, Witten in Germany, and Suez in Egypt all do throttled suction type testing. Looking briefly at the instrumentation, here we have a compound suction pressure gauge on the left. It measures both vacuum and positive pressure. Discharge gauge obviously only needs to measure positive pressure. These gauges should be installed at least 2 pipe diameters away from the pump. The readings will also need to be adjusted for the height of the gauge above the pump datum, the center line. Motor input power is usually measured by a calibrated watt meter. To get the pump power from this, you multiply the power reading by the motor efficiency. Now, this means the motor needs to be accurately calibrated. Factory test motors are regularly calibrated, and an efficiency versus power curve is produced for this purpose. If you want to use the job motor for the test, you'll need to make sure it has undergone a full performance test, not just a routine test, which is all that most production motors undergo. Alternatively, some pump test facilities use torque transducers to measure the power absorbed by the pump. This will allow you to use an uncalibrated job motor during the test. So the test procedure, first we determine how many flow points are needed to meet the test standard, API or Hydraulic Institute. For API 610 11th edition, it's a 6-point test. for API 610 12th edition, it's a 9-point test. I forget Hydraulic Institute, I think it's 6 points again. So we run the pump at each flow point and record the values as shown here. Now the reason the suction and discharge piping size is recorded is to enable the liquid velocity head to be calculated. Velocity head, V squared over 2G, is the kinetic energy of the liquid due to its velocity through the suction and discharge piping. These have to be added to the measured suction and discharge pressures. On the test sheets, the impeller diameters, including listing any underfile, overfile, or V-notching details, are shown. These are techniques for impeller machining which can adjust the shape of the curve slightly. Maybe it'll flatten it, maybe it'll steepen it, maybe it'll rotate it a little around best efficiency point. It's a bit of a black art, and hydraulic engineers and test engineers learn this over many, many years. But it's important to record these details for future spare parts reasons. So we take readings of flow speed, differential head, calculate the power, and prepare the tabulated raw data and the curves. We also take vibration readings measured for horizontal pumps at the bearing housings and for vertical pumps at the top flange of the discharge head. First test we do is always carried out with a conservatively set trim diameter on the impeller. We play it safe. It's much easier to take material off than it is to put it back on. So we'll go for a slightly larger impeller than we need, analyze the test results. This will be an internal test without the customer present. We'll evaluate it, use the affinity laws to refine the trim it, balance it, reassemble it, and at that point we will call the customer in if it's a witness test. If it's a non-witness test, we might not need to retest it. API 610 says that if the impeller diameter reduction required to meet the head is 5% or lower, then you don't need to retest. It's a bulleted paragraph in API 610, and some customers will ask us to do a retest, even if it's only a small trim that has been done. So we always do a pre-test first to make sure we're happy that everything is there before we call the customer in for a witness test. And of course, it depends on the testing tolerances, which depend on which standard you're looking at. Here are the test tolerances from API 610. Just one moment while I have a quick slurp of tea. So API 610 at the rated flow has a tolerance plus or minus 3% on head. When it's shut off, it depends on the rated head. Between 0 and 75 meters, or 0 to 250 feet, it's plus or minus 10%. Between 250 and 1,000 feet head, it's plus or minus 8%. And above 1,000 feet, it's plus or minus 5%. Rated power, 4%, plus 4%. And for efficiency, there is no actual tolerance on efficiency. And the reason for that is efficiency is a derived value. It's derived from the power. So the power is where we have the set tolerance, and the efficiency is derived from that. It is possible, if you want to have to guarantee efficiency, that could be negotiated. We'll do an efficiency guarantee instead of a power guarantee, for example. And here are the test tolerances for Hydraulic Institute, paragraph 14.6. 3 grades and basically 6 test acceptance grades: 1B, 1E, 1U, 2B, 2U, 3B. Now, grade 1 is the most stringent, and the U specifies having a unilateral tolerance band. In other words, no negative tolerance. The B specifies having a bilateral tolerance, so plus or minus 5% here. Acceptance grade 1E is a halfway house, and it's used when energy efficiency is of importance. It's a bilateral test again, plus or minus 5 here, plus or minus 3, plus 4 on power, or minus 0% on efficiency. So it's a refinement on B, which would have allowed a small fall in efficiency. Hydraulic Institute have a good white paper that you can download called Understanding the Effects of Selecting a Pump Performance Test Acceptance Grade. I put a link here to it. It's quite useful to help you decide which of these 1B, 1E, 1U, 2B, 2U, and 3B is appropriate for your circumstances. So when we've done the test, you will get a performance test curve that looks like this. It will be accompanied by the tabulated test data and calculations so that you can see how the results were achieved. When we're NPSH testing, we need to reduce the suction pressure to the point at which boiling occurs in the pump. This pressure reduction can be achieved in one of 2 ways: by suppression testing, where a vacuum is pulled on the air gap at the top of the sealed test tank, and this gives you the most accurate results. Alternatively, by the throttled suction technique, where the suction pressure is reduced by gradually closing the suction valve. You'll probably have to open the discharge valve slightly to compensate and make sure that the flow stays constant. This is not as accurate, but both are acceptable to API 610 and other industry standards. So this is what we're going to do. We're going to take 5 or 6 flow rates, and while maintaining the flow rate constant, we'll reduce the suction pressure either by pulling a vacuum on it or by throttling, all the time measuring the discharge pressure till we see a 3% drop in the discharge pressure. Then we reset for the next flow rate and repeat, and the same again and the same again until we've tested right the way across the pump performance curve. So let me just go through that again. We'll take 5 or 6 flow rates, and while maintaining the flow rate constant, we will reduce the suction pressure by pulling a vacuum or by throttling, all the time measuring the discharge pressure until we see a 3% drop in that discharge pressure, and that indicates the onset of cavitation. Then we repeat for the next flow, and then the next flow, and the next flow. Is a summary of what I just said. So here we go, 6 flow rates. First one, 126 gallons per minute. We gradually reduce the suction head, the NPSHR, and measure the discharge head. Here are the points we record. Then at this point here is where we get a sudden fall off in discharge pressure. So stop the test at that point and repeat it for the next flow, 201 gallons a minute. Then same again, 253 gallons a minute, etc. Then we determine what suction pressure corresponds to 3% head drop for each flow, and then we plot the NPSH curve. Here it is. 126 gallons a minute corresponds to 10 feet of NPSHA, and so on across the whole curve. Here's a typical test report, and you would also get the tabulated data and calculations. %3 is the pump industry standard for NPSHR, but some customers redefine it. It's well known. You could have a 1% head drop to define onset of cavitation. Occasionally, even 0%. I think ExxonMobil, I think their specification has a 1% head drop. Aramco, sometimes, well, Aramco also, I think, has a 1% head drop as standard, but it also sometimes requires that we give you an NPSHR figure based on that value of NPSHR, which will give a predicted impeller life of 40,000 hours. So that is one that our engineers, based on the history of that pump, can predict what figure that will be. But the only ones we can prove on the test bed are a 3% and a 1% NPSH test. So here's the 3% NPSH figure for this particular pump, 19 feet. Here's the 1% one, 25 feet. So quite a bit higher. 0% head drop for this pump is about 63 feet, so 3 times that value. And for onset of cavitation inception, 107 feet. So that's 5 times this figure. And according to Simon Bradshaw, the Director of Engineering at Circor, former ITT Gould as well, he says that 5 times is a good rule of thumb for cavitation inception compared with 3% head drop. So a parting thought, all pumps operate with suction cavitation. The only question is whether it's damaging cavitation. Now, I asked you a question a few minutes ago about NPSH testing vertically suspended pumps. Just have a quick look and see if anybody had any answers. No, so I'll give you the answers. But during the performance testing, the pump is suspended in a below ground suction tank or pit with an open suction bell mouth on the pump and no suction piping. So clearly you cannot pull a vacuum on the pit or throttle the suction. So to carry out an NPSH test, you need to build the pump as a one-stage pump and suspend it in the above ground sealed suction tank. You can then pull a vacuum on that tank to carry out the NPSH test. And this is what Royal Pumping does in its Tulsa factory. In some factories, a VS6 pump might be tested not in the pit, but in its own suction barrel, in the same test loop as a horizontal pump. Now, if that's the case, if you can do that, if you have a pit that you can put the barrel of the pump in and still connect it to the horizontal test loop, then you can carry out an NPSH test in the normal way, either by vacuum suppression or by suction throttling. Something else people sometimes look at for a vertical pump would be a pump down test. So for an open sump configuration, VS1, VS3 or VS6 pump without its barrel, you build the pump for the test with test shot column sections to get the length of the pump as close as you can to the minimum submergence level. So the water level in the tank is set as close as you can to the minimum submergence level. Then you run the pump without recirculation of flow back to suction, sending it to drain instead. In that way, the level in the pit will drop until the pump discharge pressure drops, indicating you've reached the minimum pumping level. This is very wasteful of water. and municipal water companies may well not allow it. So don't be surprised if the pump vendor tells you that you can't have that test. Okay, I have some photos of the Tulsa test stand for you. Let me just change the share here. This is one of the Tulsa test stands. I think we have 5 loops on the horizontal and 3 loops of vertical pumps of various sizes. We're looking at the horizontal pumps particularly here, and here is the suction vessel, which is a sealed tank, as you can see, so that we can run NPSH testing. Most of this is all self-explanatory, so I will I won't commentate on most of it. You do slides here, so I'll go reasonably quickly. You're getting these in your package, so you can look at them in more detail. Most pump companies will have variable speed drives now, so that testing can be done at full speed, whether it's a 50 hertz supply or a 60 hertz supply. Certainly all the Ruhr pump and factories have VFDs, and I'm quite sure that most major pump vendors all do as well. This pad down here allows us to assemble pumps and motors. I'll show you a little better in a slide on the Monterey factory to show you how this works. Our readouts here. Low meters. RPM. And here the suction of the isolation and control valve controls here. There is the vacuum pump connected to one of the tanks, one of the suction tanks. Suction and discharge gauges. Note the calibration dates stickers on them, so we can always check that they are within calibration. And here the Monterey test facility, the control room, the substation. And here we see a pad like I showed you on the Tulsa test with the motor mounting put on it, and it's so you can adjust pump and motor quickly as independent items and get it all nicely aligned when you haven't got a base plate installed on there. Vibration analyzer here, power meter, low meter, pressure gauges. Here again, you get a better view of that motor and pump. The pump would be mounted on these pedestals, and the motor would be mounted on here, and they can all be adjusted easily and quickly. This is the new test pit for large vertical pumps. It's a 2,000 cubic meter pit. This is a 48-inch pipeline and flow meter. Stop the chair there and go back to the one. Here we can see the new vertical pump test pit at Monterrey, Mexico. So it's under construction at the moment, so it's a work in progress. 13 meters deep, 22 meters long, 43 feet deep, 72 feet long, 13 feet wide, and holds 528,000 gallons. That's a bit more than 2 minutes retention time, I would suggest. So that pretty much concludes the fun for today. I hope you found it useful. I just get to advertise the next of the short courses. Next session is part 2 of this course on performance testing and inspection of API 610 pumps. Here's an overview of what we will be covering next time. If you look at the API 610 data sheets, there are numerous cells, the green ones, where you select various options for various inspections and tests. We'll look at, discuss, and explain most of these inspections and options. So that's on the 10th of March, 3 weeks today, 2 sessions, one for the Eastern Hemisphere in the morning, my time, and one for you guys in the Western Hemisphere in the afternoon, my time. Put that in your diary. And after that, 31st of March, that's 3 weeks later, the next session would be on startup, commissioning, and troubleshooting of API pumps, of centrifugal pumps. Okay, I'm going to leave this meeting open for a little while to allow you to post in the Q&A box, and I'll endeavour to answer those that only need a short answer here and now. Those that need a fuller answer will be answered within a few days. Anything you think of later, email to info@rawpumpen.com or direct to me, smith@rawpumpen.com. Our marketing team will direct your questions or suggestions to the best person, probably me, and they'll be sending you the YouTube recording, the link to the YouTube recording, and a PDF of the presentation with the speaker notes, as well as the summarized Q&A from both today's sessions. If you need a certificate of completion for this short course, again, info@rawpumpen.com. So let's have a look at the Q&A. I see 6 possible questions here. Let's have a look and see what we've got. Ricardo Souza says, I would like to know the best types of pump for low NPSH applications. Undoubtedly, a VS6 pump is the best pump for low NPSH applications. Next best would be a between bearings pump, a BB2, so that has a double suction impeller, and that will give you lower NPSH, but not as good as a VS6. A VS6 will get you right down to 0. Don Martinez says, based on NPSHA, when do you recommend the vacuum suppression method over suction throttling method for NPSH testing? Well, it depends on the test lab. It's simple as that. Some test labs are set up for suction throttling and some are set up for vacuum suppression. As I say, the Raw Pumpen's Tulsa factory is set up for suction suppression testing. And it's largely because they do a lot of VS6 pumps that are 0 NPSH. So you need accurate figures. But for most pump factories, I mean, our Witten factory, our Monterey factory, our Suez factory, they all have suction throttling. Now, I don't know what Gould's and Sulzer and Flowserve have. I dare say they'll be much the same. Many of their factories will be throttling and some will be suppression. Nathan Little says, where's the vacuum pump? Well, you may have seen it in one of the photographs. It's at the foot of the suction tank, and it's connected to the top of the suction tank to pull a vacuum on it. Ryan Davis says, you mentioned that the flow meter is placed on the discharge for more accurate results. What's the cause of inaccuracy if the instrument was placed on the suction? I mean, it's allowable to have it on the suction side. It's just more commonly done on the discharge side. I think you probably get less turbulence in the flow. No, I can't immediately answer that. I might need to get a question. I may need to ask that question of our test supervisors. Guan Zhang says, thanks for the presentation. What's the relationship between NPSH required and RPM? A tricky one. Many people will use the affinity laws for that, but it's not strictly accurate. It varies from it. So the simple answer is to say there isn't really one. You can use the affinity laws to get an idea, but it's more complex than that. And so you actually need to look at actual NPSH figures for that. Okay, that seems to be all the Q&A, but I've got rather a lot of chat here. So let me have a quick look at the chat and see what we have. Mostly thank yous. I see a few answers to the question I asked earlier that I didn't pick up. So a couple of you got the answers about right there. Oh, lots of thank yous. Well, thank you very much for that. I've just done what I said and asked your questions in the Q&A. There's one, okay, from Raghupathi says, in a performance test, if power meets within the API tolerance and head not, what causes parameters for the head not meeting? Well, if the head's not meeting, it's probably a blockage or a fault within the impeller. We'd have to take it down, have a look and measure the impeller and see what it is that has gone wrong, but it's not meeting the head. Could be lots of reasons: bad machining, bad casting. We'd have a look at it and if necessary, replace the impeller. Is there any impact if suction and discharge gauges elevation? Yes, I mean the difference if the suction and discharge gauges are at say 1 foot above the pump, then they'll be reading 1 foot out on the overall head. So we'd have to compensate by adding in that 1 foot. Okay, I think that is it. I don't see any. Oh, I beg your pardon. Christian Flores has come in here. What is your opinion about witnessing the test? And the question mark remote. Witnessing the test, yeah, I would want to witness a test if I were paying a lot of money for a high power pump. I might not do it for a standard pump or a straightforward pumping application, but if I were paying several $100,000 for an expensive pump, I'd probably want to pay a little bit more to go and have to witness the performance test. Remote testing is increasingly possible now. We can use cameras to record the figures. We've actually been doing that for quite a few years, so that's always an option that you can discuss with the project manager. Okay, that appears to be it. So here we go at 20 to 6. Nice early finish today for me. Thank you very much for attending today. I enjoyed preparing it and presenting it. I hope you found it useful. See you all, I hope, on the 10th of March for the next session, the second part of this session. Thank you and bye-bye.